For centuries, math was absolutely brilliant at describing things that just stood still. But what about the real world? A planet zipping through space, an apple falling from a tree, even the way a population grows. The world is constantly moving. So today, we're going to dive into the revolutionary tool that finally gave us the language to describe it all: calculus. And trust me, it's not just about boring numbers. It's the story of how we learn to understand change itself.
So, to get started, let me ask you something to sound simple. We can all figure out average speed, right? It's just distance divided by time. Easy. But what about instantaneous speed? The speed of a ball at the exact moment it hits the ground. Think about it. In a single instant, 0 time passes, and 0 distance is covered. Suddenly you're stuck trying to divide 0 by 0, which is, well, impossible. This little problem stumped the smartest minds for centuries. So how on earth do you solve it?
Okay, so to even begin to crack that riddle of instantaneous change, we first need a way to talk about change itself. We need a precise language, something to connect cause and effect, like time and an object's position. And in the world of math, that language is built on this really elegant and surprisingly simple idea called a function. A function is really the fundamental building block of all of this. It's basically just a rule that takes an input, let's say time, and gives you one single unique output, like the position of that falling ball. You can almost think of it like a machine. You put a number in one end, the machine does its thing, and a new number pops out the other side. This is the grammar, the basic set of rules we're going to use to describe our world in motion.
And of course, there are all kinds of functions out there to describe different relationships. You've got your linear functions for straight lines, quadratic ones for those nice curves, and then you have the wild ones, like exponentials for explosive growth. Each one tells a totally different story about how things change.
All right, so now we've got our language, functions, but we're still facing that divide by 0 brick wall. How do you analyze a single instant? Well, the big breakthrough came from a huge shift in thinking. Somebody asked, what if instead of trying to land exactly on the point, we just get infinitely close to it?
And here's that paradox laid out plain and simple. An instant? It has 0 duration. A point on a graph? It has no width. So, how can you possibly measure a rate of change, like speed, at a single 0-width point? It feels like it should be impossible, right? And for a very long time, this was the wall that mathematicians just kept running into.
And then someone came up with the brilliant, elegant solution, the limit. The whole idea is just to change the question. Instead of asking what happens at this point, which we know leads to dividing by 0, we ask a different question. What value is our function approaching as we get closer and closer and closer to that point? See? By looking at the trend, we can figure out what the value should be at that point without ever actually having to do the impossible math. It's such a clever workaround.
Okay, so now we're armed with our 2 secret weapons, functions and limits. And with those, we can finally go back and solve that first huge problem of calculus. We can actually measure instantaneous change. And this brings us to one of the 2 main pillars of calculus, the derivative.
So what is the derivative? It's simple. The derivative is that instantaneous rate of change we've been hunting for. It's the speed of our ball at the very millisecond it hits the ground. And if you think about it visually, it has this really cool, beautiful interpretation. It's just the slope of a straight line that perfectly kisses the curve of our function at that one single point.
And you can really picture how this works. Imagine you draw a line that cuts through 2 different points on a curve, okay? Now, using that idea of a limit, you start sliding one of those points along the curve, getting it closer and closer to the other one. As that distance between them gets infinitely small, approaching 0, that line starts to pivot until, bam, it just barely skims the curve at one single spot. That final line is called the tangent, and its slope, that's your derivative. That's the rate of change at that one single instant. Amazing, right?
Okay, so derivatives are all about breaking things down, right? Zooming in on these infinitesimally small moments to see how fast something is changing. But calculus has a whole other side to it. What if we want to do the exact opposite? What if we want to add up an infinite number of tiny little pieces to figure out the grand total?
Like, for instance, how would you find the exact area under some weird squiggly curve? There's no easy length times width formula for something like that. This is the second huge problem that calculus was built to solve, the problem of accumulation, of adding things up. And the approach here is just as clever. We start by just approximating. We slice up that weird area under the curve into a bunch of skinny rectangles, because we do know how to find the area of a rectangle. Then we just add them all up. Now, if you use the left corner of each slice to set the rectangle's height, you'll be a little bit under. If you use the right corner, you'll be a little bit over. But hey, it's a start, right? We're in the ballpark.
But this is where the real magic happens. We bring back our old friend, the limit. What if we make those rectangles infinitely thin, and we add an infinite number of them? As we do that, those little errors, the bits where we were over or under, they shrink down to nothing, to zero. And the limit of that infinite sum gives us the exact area, no approximation. This incredibly powerful tool for summing up infinite pieces is the other pillar of calculus, the integral.
So let's recap. We have these two massive ideas. On one hand, the derivative, which is all about finding instantaneous rates of change by breaking things down, and on the other hand, the integral, for finding the total area by adding things up. And for a long, long time, people thought of these as two completely separate, unrelated tools. But then came the biggest, most mind-blowing discovery of all.
Think about it. On one side, you've got differentiation, that's breaking things down. On the other, you have integration, that's adding things up. One problem is find the slope. The other is find the area. I mean, they look like they're from completely different planets, right? Solving totally different problems with totally different methods.
And this is the fundamental theorem of calculus. And when it was discovered, it was absolutely earth-shattering. Because it turns out that these two processes, slicing things up and adding things up, are perfect opposites. They literally undo each other, just like multiplication undoes division or addition undoes subtraction. Finding the slope of a curve and finding the area under it are two sides of the exact same coin. This insight was the key that connected everything and unleashed the true power of calculus on the world.
Okay, so cool theory, right? But why does any of this actually matter in the real world? Well, because this beautiful kind of abstract idea is the engine running behind the scenes of our entire modern world. It's not just some toy for mathematicians. It's a practical tool that gets used everywhere, every single day.
I mean, think about it. The power of the integral lets us add up all those infinite pieces to solve very real problems. You want to calculate the exact length of a curvy road for paving? That's an integral. Need to find the precise volume of a weirdly shaped part for a jet engine? Integral. Even something like figuring out the total energy a city used over a day. Yep, that's an integral too. It's the ultimate tool for measuring totals in a world that isn't made of perfect squares and circles.
So, in the end, our whole journey brings us right back to where we started, with that puzzle of change. We kicked things off with a simple question about a falling ball, and from that, we uncovered this incredible mathematical language that lets us describe the entire universe in motion. Which, of course, leaves us with one last, really big question to chew on. If calculus is the mathematics of change, what else out there can it help us discover?